We'll finish up our discussion of the mean value theorem by taking it a bit further and looking at some other consequences to the theorem itself. This is going to lead us into a couple of new definitions, antiderivative and antidifferentiation. And along the way, we're going to see some new theorems about the derivative of a function being zero and functions having the same derivative but differing by a constant. So we begin with this. We know that constant functions have the zero function as their derivative. Yes, we do. We know that if we have a function f of x equals a constant, say 5, then f prime of x is equal to 0. And we could replace that 5 with any constant, positive, negative, as long as it's a real numbered constant. Well, we can now use the mean value theorem to show the converse, that actually the only functions with the zero function as their derivative are constant functions, meaning that if we start with f prime being 0, then the only functions that could possibly have that function as their derivative are constant functions. And here's that corollary to the mean value theorem. If f prime of x is equal to 0 at each point of an interval I, then there exists a constant c for which f of x is equal to c for all x in I. That means if we know the derivative of a function is 0, then we also know that that function must be a constant function. So then that corollary leads us to a further thought that we can show that if two functions have the same derivative, that they only differ by a constant. So here we are. If f prime of x is equal to g prime of x at each point of an interval I, then there exists a constant c such that f of x is equal to g of x plus that constant for all x in I. Let's summarize that real quick again. If we have two functions that have the exact same derivative, in other words, if f prime of x is equal to g prime of x, then those original functions, f and g, only differ by some constant value. For example, we know the derivative of f of x equals x squared is 2x. In other words, f prime of x is 2x on the interval negative infinity to infinity. So any other function g of x that has a derivative of 2x must have the formula g of x is x squared plus c for some constant c. Let's think about that again. If we know that f prime of x is 2x, and we know that g prime of x is 2x, they have the same derivatives, then f of x might be x squared, and g of x has to be x squared, maybe plus a 5, plus a 2, plus a 3, but they only differ by some constant value. So here's an example where we can apply that corollary. Find the function f of x whose derivative is sine of x and whose graph passes through the point 0, 2. So a function whose derivative is sine of x. So we know right now that f prime of x is equal to sine of x, and we are looking for f of x. Well, we know then that if there are two functions that have the same derivative, so let's imagine there's another function g prime of x that also has a derivative of sine of x, that the two original functions only differ by some constant. So f of x would be, well, let's think real quick, what function would have a derivative of sine of x? Let's see, we know the cosine's derivative is negative sine, so we must be looking at negative cosine of x here. Actually, I wrote that wrong. This should be a g of x. And then the f of x would also be a negative cosine of x, but it would differ by some constant. So these two functions being the same, or any two functions being the same, only differ by a constant. So we're here first. F of x has to be negative cosine of x plus some constant. But we also have been given some extra information that this graph passes through the point 0, 2. So if we plug in the x value of 0, our function should give an output of 2. So let's try that. F of 0 is negative cosine of 0 plus some constant, and then the result should be 2. So cosine of 0 is 1, so now we have -1 plus a constant is 2, which means that that constant must be 3. And now we can write that final answer that this function must be negative cosine of x plus a 3. And that's the function we're looking for. It's called a particular solution to this type of equation, and we're going to see that here real quick. This exercise I'm going to leave to class time. It's exercise 35 from your text, and we will work it then, not in this video. Here's back to the main idea. In the example we just did, we were given a derivative and asked to find a function that has that derivative. This type of procedure is so important that it's actually given a name because it's referred to so often. That name is antiderivative. A function capital F of x is an antiderivative of a function little f of x if the derivative of capital F of x is equal to the function little f of x for all x in the domain. The process of finding that antiderivative is called antidifferentiation. In other words, you begin with a derivative and you want to find a function. So I'll even write that here in the notes. Begin with derivative, find function. So it's really just going through differentiation in reverse. Rather than starting with a function and finding its derivative, start with the derivative, find the function. Now we know that if f has one derivative only, then it has infinitely many antiderivatives because they all differ by a constant. That last corollary says that this is all there are. In example 7, we found, like I said before, the particular antiderivative of sine of x, whose graph passed through the point 0, 2. There is another example after this, but we're going to save that for class time or a separate video, and that ends our discussion of the mean value theorem.